Welcome back, everyone. Okay, let's jump straight into this explainer because today we're tackling the single biggest physical threat facing modern data centers right now. As artificial intelligence and high-performance computing literally take over the world, we're hitting a massive physical wall. The hardware is incredible, sure, but it's generating an absolutely unprecedented amount of heat. So today, we're going to break down exactly how to solve this massive thermal bottleneck.
700 watts. Let that sink in for just a second. That is how much power a single modern GPU can consume today. I mean, we used to worry about entire servers pulling that kind of wattage, and now that's just one graphics card. As processing power skyrockets to handle these massive AI workloads, the inevitable byproduct is an absolute heat wave.
And that brings us to the ultimate engineering question, right? If you take a standard system today, let's say 2 CPUs and 8 of those 700-watt GPUs, that single machine requires about 7 kilowatts of cooling capacity all by itself. How do you physically extract that much heat before the silicon literally cooks itself to death? The traditional answer has always been air, but as we're about to see, the laws of physics are really starting to disagree.
Here is our roadmap for this explainer. 1. The data center heat wave. 2. Why liquid beats air. 3. The bottom line. 4. 3 ways to cool. And finally, number 5. Choosing your cooling strategy.
Let's kick things off with Section 1, the data center heat wave.
The crucial thing here is understanding the sheer scale of the problem we're facing. The most powerful CPUs are now hitting a thermal design power of up to 400 watts. Add in those 700-watt GPUs, and you're looking at that staggering 7 kilowatts of heat per system. Now, traditionally, you'd cool this by forcing massive amounts of cold air over the chips using fans. But fan size is physically constrained by the geometry of the server itself, often just 1.75 inches or a single U in height. We're literally running out of physical space to cram bigger fans into these tiny metal boxes. It's just no longer a mathematically viable solution.
And if you fail to manage this heat, you get what engineers call jitter. It's thermal throttling. Basically, when a chip gets dangerously hot, it goes into self-preservation mode. It actually reduces its own clock rate or completely shuts off processor cores just to avoid melting. Think about what that means. You're paying top dollar for world-class computing performance, and because of heat, your system is intentionally slowing itself down, completely destroying your application throughput.
Which brings us nicely to Section 2, why liquid beats air. It all comes down to the fundamental difference between how air and liquid actually work. Air cooling essentially relies on brute force, massive, super energy-hungry fans blowing desperately over hot chips. But liquid utilizes completely different physical properties. Because the molecules in liquid are packed so much closer together than in air, liquid is highly conductive. It's just inherently scientifically better at transferring heat away from a source.
And we're not talking about a slight improvement here. Liquid is orders of magnitude better. Water actually has 1,000 times more cooling capacity than air. 1,000! And on top of that thermal conductivity advantage, it actually takes 10 times less transport energy to move that heat away. That means you're doing vastly more cooling work while spending significantly less electrical energy to do it. It's a huge win-win.
All right, let's get into Section 3, the bottom line.
Because at the end of the day, thermodynamics has to make financial sense, right? Let's talk about the cost comparison for a server rack filled with 8 of those intense 8 GPU systems we mentioned. With traditional air cooling, you need a whopping 84,000 watts of power per rack, mostly because of the massive air conditioning overhead. That gives you a power usage efficiency, or PUE, of about 1.5. But with directed chip liquid cooling, because you're eliminating those internal fans and room air conditioners, the power needed drops to just over 55,000 watts. That tightens your PUE down to a hyper-efficient 1.1. So, in just 1 year, your total kilowatt-hour cost plummets from roughly $735,000 to about $485,000. Honestly, I couldn't believe this number when I first saw it. $60,067. That is your pure 3-year net savings for a single rack. And that's after you factor in the estimated $30,000 upfront cost to implement the liquid cooling system in the first place. It pays for itself and then generates over $60,000 in operational savings per rack. If you've got 10 racks, you're looking at over $500,000 in pure savings.
So just to summarize these incredible financial rewards, Switching from air conditioning to effective liquid cooling can reduce your OPEX by more than 40%. It drastically drives down your PUE, and it offers an average facility investment payback of literally just 1 year. But beyond your wallet, it radically lowers power usage overall, which directly reduces carbon emissions from fossil fuel power plants. You're basically saving huge amounts of money while simultaneously crushing your corporate environmental responsibility goals.
Moving right along to Section 4, 3 ways to cool. So how do you actually implement this? The first way is direct-to-chip, or D2C. This is a closed-loop system. Instead of blowing air, you use a thermal transfer material to attach a cold plate directly onto the top of the running CPU or GPU. Then, a small pump circulates cold liquid right over that plate at the precise source of the heat. The liquid absorbs the heat instantly and carries it away. The really elegant part about this liquid-to-liquid loop is that the hot liquid is piped completely away from the servers to a cooling distribution unit. The heat is moved entirely out of the server rack and cleanly transferred to the building's external cooling tower. You aren't just blowing hot air around a room anymore. You're surgically extracting heat from the chip and piping it straight outside.
Now, the second method takes things to the absolute extreme: immersion cooling. For environments dealing with staggering heat densities, or maybe confined spaces that just don't have traditional data center infrastructure, you literally submerge the entire server hardware into a tank. Use a highly specialized, non-conductive and non-corrosive fluid, of course, so it doesn't short out the electronics.
The heat removal flow here is just brilliant. The submerged components directly transfer their heat to the fluid. As the liquid warms up, it naturally rises to the top of the container, where it's pumped out, run through a heat exchanger to be chilled, and then gracefully cycled back in. It is incredibly efficient. And the best part? It operates with virtually zero noise. And finally, the third option is the rear door heat exchanger, or RDH. This is basically your least disruptive method. If you don't want to run tubes of liquid directly to your silicon chips, you instead replace the back door of your server rack with a liquid-cooled radiator door. The traditional server fans still blow hot air out the back, but that air immediately passes through the chilled door, cooling it down before it ever even enters the data center room. It's a fantastic transitional step to drastically reduce your need for those giant room air conditioners.
And that brings us to our final section, number 5, choosing your cooling strategy.
The source material lays out this brilliantly simple rule of thumb progression based on your total heat load per rack. Step 1, if your rack is only generating up to 25 kilowatts of heat, traditional airflow is probably still sufficient for now. Step 2, once you cross into that 20 to 45 kilowatt zone, direct-to-chip becomes an excellent, highly efficient option. But step 3, if you're pushing above 40 kilowatts per rack or operating in a highly confined space, immersion cooling really transitions from being an option to being practically required.
The good news is the hardware industry is totally prepped for this shift right now. Solutions like Supermicro's product line come ready-made with these cooling loops seamlessly integrated. You've got the Hyper series optimized for maximum compute in tight 1U or 2U spaces. The Big Twin packs 4 nodes into a 2U enclosure with shared power and cooling to maximize those resource savings. The Superblade can pack up to 20 blades in an 8U chassis with direct-to-chip coolers routed directly through the infrastructure. And naturally, they have dedicated GPU systems designed specifically for massive AI and HPC workloads. The hardware is ready when you are.
To wrap up our explainer today, the main takeaway is simply this: next-generation processors are only going to consume more power and produce more heat. As HPC and AI move into mainstream workloads, liquid cooling is no longer just a nice-to-have optional upgrade. It's rapidly becoming the critical enabler. Without it, you are inevitably going to hit a computational brick wall of thermal throttling and spiraling energy costs.
Which leaves us with one final, pretty urgent question. Take a look at your own infrastructure. With AI demand surging and your hardware running hotter than it literally ever has before, can your data center actually afford to keep relying on air? Thank you so much for joining me for this explainer, everyone, and I'll catch you on the next one.